I think hopefully more will be able to join, but just in the essence of time, let's get going. So first of all, thank you so much for joining. This is the Rapids workshop where we'll be talking about using GPUs to accelerate data science with Dask and the PyData ecosystem in general. So for those who might not be or have not attended a workshop yet, which I hope you have, they've all been great, the ones that I've attended. Just kind of go over the overview. It's a 2-hour block of time where we'll be talking about various topics, but all under the same theme. So this theme is GPU acceleration in the PyData ecosystem, as well as Rapids particularly, right? So kind of what we're going to talk about today is kind of, for those who don't know Rapids, provide an introduction, then kind of go all the way to the usage in the enterprise. So I'll be giving an introduction to what Rapids is. For those who might not know, hopefully it's great information. For those who might know, hopefully it's a nice reminder or refresher, or hopefully you gain some new insights. And then pass it off to my colleague Vibhu, who's going to talk about accelerating common end-to-end workflows, where you'll see a little bit more at a code level what it looks like to implement Rapids. Then he's going to pass it off to our colleague Devin, who's going to talk about getting started with native Dask tools to get up and running on NVIDIA GPUs. He'll be talking about kind of smaller scale examples to larger scale examples on Kubernetes. And then we're going to pass it off to Peter, who's going to talk about some really exciting developments in the GPU accelerated ecosystem, very similar to how people are building tools upon Dask. People are doing the same with both Dask and Rapids. So some really cool examples there. And then we're going to pass it off to some of our organizational partners in crime, particularly Richard Ulrich from Walmart, who's been a big proponent of Rapids for a while now, as well as my former colleague, Mike McCarty from Capital One, who's been helping to really push Dask and Rapids and just the PyData ecosystem internally at Capital One. We'll close things out. We may or may not have time for questions. I think we will, which would be great. So we can kind of have a little bit more interactive Q&A session here. And if we don't, there is a follow-up channel, or there's a Slack channel that we can all kind of continue the conversation in, and hopefully we do. So for those who might not know, I guess quick, let me do an introduction. I'm Jake Schmitt. I'm a product marketing manager at NVIDIA, particularly with the enterprise data science products team. Formerly I was with Capital One, where I was helping to drive the adoption of Dask and Rapids there, which was the natural transition to NVIDIA now. But for those who might not know what Rapids is, it's a collection of open source tools that speed up end-to-end data science entirely on the GPU, the NVIDIA GPU. And Rapids provides a variety of libraries that accelerate common tasks, such as data preparation, machine learning, graph analytics, as well as data visualization. And beyond those task-specific libraries, Rapids also offer libraries for specific domain problems, right? So we have a library or packages for cybersecurity, spatial data analysis, signals processing, as well as image processing. Before we kind of get a little bit deeper into Rapids itself, let's take a look at how things have evolved in data processing and big data analytics in the last, honestly, 20 years. So over the last 20 years, the practice of big data analytics has grown extensively. Well, the concept has been around for a while. The advent of Hadoop, the creation of Hadoop in the mid-2000s really marked the advent of the big data practice. In 2018, as we all know, Spark came around and really kind of improved that practice by requiring a little less code, keeping processing in memory, and also supporting a variety of languages. Kind of while this is happening in the late 2000s, researchers, with the advent of CUDA and the release of CUDA, as well as the concept proliferating of GPU, which is general purpose graphical processing unit, we're starting to see researchers really start to leverage GPUs for intensive deep learning workflows. In the highly parallel architecture of GPUs really lends itself well to the highly parallel nature of data science. But we noticed that keeping analytics entirely on the GPU is pretty challenging, and a practitioner more or less needs to know CUDA to be able to really leverage the power of GPUs. What Rapids aims to do is make it easier to leverage GPUs for data analytics. We're meeting some of the traditional pain points of consistent GPU reads through building on top of Apache Arrow, and also accelerating popular data science tools, eliminating a significant learning curve for GPU operations. So while Hadoop's really fueling this evolution in big data, the tools that we all know and probably brought us here to the Dask Summit, like pandas, scikit-learn, matplotlib, are really starting to make data science more accessible to a broader audience. And while these usable tools are becoming popular, data collection and analysis is becoming more and more sophisticated, and it's really growing the prevalence of big data use cases. And these tools, pandas, scikit-learn, are really great, very comfortable, and have a great user experience for smaller to medium data use cases. Big data use cases can kind of be particularly frustrating, as we've all probably experienced. And luckily, Dask came along, I think about 5 years ago, official release in I think 2018. Really injects this really popular ecosystem with parallelism, making taking it a user experience that people like and making it a lot more easy to use it for larger scale use cases. But relying on larger scale CPUs is kind of really reduces the feasibility of some way of large scale data analytics. Having a large set of CPU clusters or CPU racks is really costly, and it can also present overhead that can make a project more challenging. And so what Rapids really tries to do is harness the power that was seen from the late 2000s on in deep learning, the prowess that's been seen there, and leveraging it for traditional data science workloads. And like Dask, Rapids really sticks to the tenets of building on top of ecosystem standards, PyData ecosystem standards. So folks feel very familiar even when they're using an NVIDIA GPU. And so people who feel proficient with pandas or scikit-learn won't really have to learn too much to start being able to operate well on these GPUs. And Rapids also pairs very nicely with Dask, which allows for vertical scaling with Rapids, so a very strong instance or hardware underneath to power your operations, but also allowing you to horizontally scale and distribute with Dask. So you can scale out to a multi-node, multi-GPU cluster, really just churn through some of these big data processes. And so as an example, here's a few, simplistic, but examples of that quick transition from something like Pandas or NetworkX to a Rapids library. We really want to keep it as familiar as possible so folks feel like they just kind of already know the syntax and just kind of make a few slight changes to really operate well and effectively on the NVIDIA GPU. So, obviously hardware and your setup can really kind of affect the performance improvements that you have, but even on maybe a smaller cloud instance or a larger scale cluster, we see some pretty significant speed ups on just this quick change. So taking it from just the task level speed ups to a more end-to-end performance or end-to-end life cycle, we see really significant speed ups, right? So going from your data cleansing, your loading, to engineering features, to training and classifier, all those speed ups at each of those different pieces really adds up, and we see really significant performance improvement at the end to end. So really with Dask, what it allows us to do is that scaling out, and we see some serious improvements on benchmarks that we've run. We usually, every release or so, do a mortgage benchmark on a 200 gig CSV data set, where we do an end-to-end workflow where we're cleansing data, engineering features, and training a classifier. And we see some significant speedups against 20 CPU node setup to 100 CPU node setup. So our latest architecture, the NVIDIA A100, we're able to use 16 of those to get the same power as a CPU node. And to compare to a 20 CPU node, a very comparable configuration to the 16 A100s that we're seeing a 7 times performance improvement. And that also lends to a more cost-effective solution. So the performance to cost solution is 20 times more performant on the NVIDIA GPU. And what we're also seeing is we really try and focus on software and hardware holistically, right? And we can see performance improvements over time because we're thinking about the two together. Even since the initial release of Rapids 2.5 years ago, we're seeing three times more performance than the initial benchmark that we ran. And that also lends itself to a 7 times improved total cost of ownership improvement. So better cost performance ratio. And as we're starting to see Moore's law start to slow down, this holistic mindset becomes even more important for fueling continued innovation in data science. By building Rapids holistically, users can benefit from new hardware as they get released through a very familiar tool set. And I'm going to pass it off to my colleague Vibhu. He's going to talk more about, at a code level, what it looks like accelerating these common end-to-end workflows. All right, Vivo.
Hey guys, so this is Vidhu Java, and today I'll be talking about how you can accelerate your common end-to-end workflows using Rapids and Dask. I am a software engineer and data scientist with NVIDIA and have been here for about 2.5 years. So before dwelling more into how you can accelerate your workflows, let's try to understand how these workflows actually look like. Your workflows often involve feeding your data into memory. This with Rapids, almost most major formats like CSV, Parquet, JSON, or GDF are supported. And once you read that into memory, you'll do some feature engineering. Here, Dask along with QDF comes into play, which you use for doing your ETL and feature engineering. And then you can hand over your data to a machine learning algorithm. And this is also scaled up and scaled out using Dask and Rapids using QML. An important thing to note about such workflows is that the primary bottleneck in big data isn't the exciting modeling part, it's often the pre-processing bits. And this problem is gonna grow further and further as we go on because the data sizes continue to increase. And if you really want to interactively play with your data, you essentially need to resort to some techniques like histogram, like taking sampling your data using histograms, distributions, dimensionality reductions. And doing all this comes at a cost of accuracy and isn't really scalable. So if you can actually accelerate your ETL by a lot, which means that you often get more accurate models and have a better idea on how your model will do into production. So now I'll directly go into a workflow that I'll walk over today. So in this workflow, we are working with NYC taxi dataset. Here we are processing about 380 million rides in NYC from the year 2015 to the year 2017. So I am gonna do this first on a CPU cluster with about 96 workers. And like so essentially this is for a 48 physical core 96 virtualized core machine. And the first thing that we do is we read in the data using Dask data frame. Then we clean it up a bit, like we ensure that all the data types line up. And because this data is spread over time, the schema change over time, and which is very often in real world data. So we ensure that everything just lines up. Once we have done that and handle those changes, we do some exploratory data analysis on it. We filter out some outliers using certain filters. And once we have that, then we go on to add interesting features to the data set. So the features that here we add are the year, month. So as you can see here, we are using like the same pandas slash dash data same API that we really like. And this won't change when we go on to use Dask and Rapids together. So these are like the datetime features that we add time duration, etc. Another important feature that we add in this workflow is the haversine distance. So haversine distance is essentially a distance between two latitudes and longitudes around the globe. And so essentially a distance on a curved surface. If you are a flat earther, you're gonna use the Euclidean distance, but we are all not flat earthers here at NVIDIA, so we use a curved distance. So once you have done that, we go on to run ETL on it. So let's actually see what that, just a second, what the Dash dashboard is looking like. So here we are essentially, we run a task and we are running it on about 96 workers, as you can see, and each task is taking about 3.7 seconds on about 96 workers that we have. So yeah. yeah, while the task runs, let's actually look at what we need to do to transform this workflow to suit better to GPUs. So on all the API changes that you need to make first involve with the cluster setup. With Dask CPU, you use Dask or distributed local cluster, but with GPUs, you use a local CUDA cluster. Everything else almost remains the same, but with local CUDA cluster, we follow a one worker per GPU model. So while we have 96 workers here, with local CUDA cluster, you have as many workers as the number of GPUs in the machine. On an IO front, we use on CPU Dask.data frame. On GPU, we use Dask_QDF. Everything else remains the same. And on the feature engineering front, so if the features that you want to engineer are outside the standard pandas as data frame API that you're using, on CPUs, you'll often use NumPy to create these features. The equivalent of doing this on GPUs will be done using CuPy. So essentially, you change your import statements as import CuPy as CP and replace the NumPy as NP with CP, and everything else remains the same. And the code will just work on GPUs. The next thing we'll go on is about how you can accelerate your training. On CPU, the method that you use is histograms. On GPU, you use GPU_histogram. On CPU, you use CPU_predictor for finding predicting, and on GPU, you use GPU_predictor. Now let's actually switch to the GPU version of the notebook. As you can see here, like almost all of the code is as is, apart from the import statements and the changes that I mentioned. And let's see how quick it actually is. So the other notebook took about 57 seconds for ETL on our really meaty CPU cluster, but for GPU, it's become really quick. Oh, so yeah. Oh, and it already finished on the GPU. So it took about 5.25 seconds here now. Let's actually look at the GPU dashboard that we have. So this shows that this is the amount of memory that you reserve on the GPU using the pool. You have about 16 workers. Now actually, let's look at that task stream. So there we know that the task essentially took about 3.5 seconds, and that task was for was on a small chunk and was on a smaller chunk of data. On a smaller chunk of data. But with GPU, we used a bigger chunk of data, but we were still on an individual task level really, really fast. Then we essentially go on to train our model, and then we try to see which of our features are important and save a model for future purposes. So essentially with the minimal API changes, we became about 13x faster on ETL and 6x faster for training. So the conclusion that you can draw from this is that GPUs can provide a lot of cost savings, as well as allows you the ability to interact with big data in real time. This is really important because now you can have a very quick iteration speed when you're testing your hypothesis. So the speed of exploration uh, often leads to better solutions for your machine learning models. Before I leave, I'd like to share some tips that you can use to fine-tune Dask for rapids. So, like the first thing to note is partition size really matters. With GPUs, as your inherent computational unit now becomes really parallel, you can now use larger partition sizes. This improves your GPU utilization and reduces scheduler overhead. The memory pressure when you are scaling your GPU, scaling your workflow across GPUs is very real. This is because GPUs are often more limited in memory than the CPU memory. So you should really think about how how your data types are. So you should be downcast your data types when appropriate. You should avoid materializing indexes because they often eat into memory. You should, and also sometimes if you can add explicit synchronizations, they can reduce memory pressure because once you have added that synchronization, you can get rid of some of the data that's no longer needed. On another thing to note is because everything is now really parallel, if you can convert your shuffle joins into broadcast joins, it becomes really fast. And then on an IO front, you can often convert to a single partition after IO if you have a lot of small data frame. This again comes back to the fact that because your GPU itself, a single GPU is that parallel, you essentially get more acceleration out of it. And if you want to parallelize across more GPUs or tasks, you can split your data by row groups and for your parquet data by row groups and often get better parallelism. Now I'll hand this over to Devin, who will talk about how you can use native Dask tools to get started on GPUs.
All right. All right. So I'm Devin Robinson. I am a data scientist at NVIDIA, and I'm going to go through the process of using Dask's native tools, specifically some of the cluster managers, to get started using NVIDIA GPUs. For this process, we're going to go from workstation to cloud scale. We're going to start off with kind of a motivating workstation example, something you might do in your own type of workflows. If you want to generate a proof of concept, design your code, prototype, and just test to make sure that it's doing what you expect it to, that the accuracy is where you want it to be, and that everything looks good. Once you get to that point, if you want to start looking at maybe larger data sets, you want to start exploring whether or not you can get improved training times by scaling to multiple nodes. And you have additional, say, like ad hoc hardware on site, you have VMs or something that you can just kind of throw together to test out the scaling of your system. Then we might want to move to something like Dask's SSH cluster manager. All that's going to do is essentially allow us to specify some number of machines, and Dask will go out and create workers and schedulers on each one of those. And then finally, you've gotten to the point where you've tested some setup or some workflow you have. It looks like it's good on multiple nodes, and you're ready to start training either at scale or testing with various kinds of hardware. We're looking at things like that for serving inference or something. Then we can move to the cloud. And for those use cases, we're going to demonstrate that using Dask Kubernetes with the Google Kubernetes engine as an example. I'm just going to go from there. All right, as a motivating example for what we're going to do, we're just going to walk through a simple example of using XGBoost to predict taxi fares. To go about this, we're going to first obtain a data set, first locally, and then we're going to use one that's publicly hosted on GCS. We're going to be working with the 2015 Parquet data set for the New York City taxi data. Next, we're going to go through the process of doing some light ETL, going to import, clean the data set, persist it out to our workers. This is just going to consist of making sure that our data types are correct, any type of NA fills that we need, and then a little bit of SQL to restrict or remove outliers and kind of restrict the geographic area that we're interested in. Once we've done that, we're going to train our XGBoost model to predict the price of an individual cab ride. And then we're going to take that trained model and use it to perform inference in a number of different situations. The first, we'll be using XGBoost standard predict method. The second, we'll be using Dask's in-place predict method, which allows us to save a little bit of time by letting us skip doing the D-matrix construction. And then finally, we'll look at a rapid specific method that uses QML's forest inference library, FIL for short. And what this does is it allows us to wrap a saved or a serialized XGBoost or random forest model and essentially accelerate it for specifically inference tasks. All right, so again, we're going to go through this process on both local CUDA cluster, SSH cluster, and then a cube cluster. And this will show a progression from using something like local storage with a single GPU to potentially replicated storage. In the case of the SSH cluster, we're just going to use a single node to illustrate the process, but it scales up kind of from there. And then finally look at using distributed storage with cube cluster, multi-node, multi-GPU, and potentially a range of hardware resources, and just kind of show the progression there and how we can handle the different situations as we get a little bit more complicated. And what we're going to see is that in each case, while the cluster setup is different, the actual operations that we're going to go through once we've got our cluster set up and we're ready to actually train our model using existing data is all the same. So it's a very nice kind of easy way to progress. Okay, so to start, if we imagine we're on just kind of a local workstation, we want to get up and running and test out training a model using GPUs and just get everything together, make sure it all makes sense, and we kind of prove out some concept we're trying to do. It takes basically 3 lines of code. Once you've got your Dask CUDA library, all you do is import the local CUDA cluster object. You're going to create a cluster with that just by instantiating it. And then we wrap that local cluster with a Dask client, and that's going to enable us to issue commands and develop workflows and kind of pass in all of our relevant information. The next thing we're going to need to do is we're going to download our data set. So on your local machine, we're essentially just going to hook into the publicly hosted taxi data set using Google's GCS-FS file system libraries for Python. And so it's really straightforward. All you do is you're going to create an instance of GCS file system, and then you can just use their API to essentially clone the NYC Parquet dataset. Once that's done, you're going to see something like this locally, standard Parquet layout, and it's about 21 gigabytes of data. All right, so next we'll build up just a quick function that does our ETL. We're going to eliminate, at least on the slides, most of the kind of the non-interesting features. There's some field remapping. We're basically defining columns that we have to have, and then some SQL query fragments that are going to allow us to trim it down to the right geographic region that we want, things like that. So go through that process, and then we have a little bit of extra functionality here where we've defined another function, so we can essentially, once we've defined the workflow that we're going to use to kind of load and clean the data, we can persist that specific Dask data frame out to all of our workers. And this function is going to allow us to do that, as well as potentially persist a different sized inference data set as well. For our purposes, we're just going to use the full data set for both the train and inference tasks. All right, so once we have all of our ETL code ready, we can go ahead and load our training and inference data sets using the function we've just created. And all it's going to take is a client and the Dask data frame that we're interested in using. Okay, so if you're using something like Jupyter Notebook and you have the Dask lab extension, once you run this command, you'll be able to see something like this. So kind of the real-time progress of what's going on, where we see the Parquet file being read in, and we see the trailing manipulation tasks. So assigning data sets, changing data types, and then dropping NAs, things like that. So it can be a really nice tool to use when you're wanting to make sure that things are going the way you expect, and that everything's happening as you anticipated. So from there, we take our loaded data set and we're going to wrap it in a D matrix, which is just kind of a format that XGBoost training framework requires. In this case, it's going to be a 0 copy operation. It's just going to kind of change the interface so that XGBoost knows how to use it. All right, so we'll go through that, and we're going to train our existing model on that data set. It'll go through some number of iterations, and then after that, we will get it'll train, in this case, 130 seconds. All right, so at this point, we've gone through, we've downloaded our data set. We have train an XGBoost model using it, and we're ready to look at using that model we've trained for inference. So out of the box, Dask is going to offer Dask XGBoost rather is going to offer two methods for doing this. We've got the standard predict method, where we create a new D matrix with our inference data frame, and then we call XGBoost Dask predict. That's going to go through. It's going to kick off a task called dispatch predict, along with some other coalescing tasks and some things that you can see here. And that's going to take about five seconds to finish. The other option that we can do is we can use Dask's XGBoost in-place predict, which is essentially going to save us a little bit of time because it allows us to avoid having to create a D matrix, and it reduces, I guess, some of the additional metadata that we have to deal with. So we run that, we see basically a 31% improvement on our single node prediction times. Okay, so the final kind of inference method that we can look at is using the rapid specific forest inference library for prediction. And what this does is it's going to allow us to take an existing save model, either an XGBoost or random forest model, and wrap it in a structure that's designed to accelerate inference. And in many cases, kind of the performance improvement can be quite good. As it stands now, the forest inference object can't be serialized by Dask directly. So instead, what we're going to do is we're going to save off the model to, in this case, just local storage. When we move to the Kubernetes framework, we'll use some type of distributed storage. But then what we're going to do is run an out-of-band task. And in this case, essentially attach fill to worker, which is going to cause each of the workers in our cluster to read that stored model and instantiate a fill object in their own local persistent memory. And what that does is that later on, if we want to use that model again for prediction, we can pass in some proxy function, in this case, something like predict on worker, which is just going to allow us to tell the worker that for whatever data it's going to receive, that it needs to load, or it needs to use its fill model to do prediction on that data. And so we go through this process of saving off our XGBoost model, running this out-of-band instantiation process for each of our workers to build its own fill model. And then what we can do is take something like our inference data and call map partitions on it with our predict on worker proxy. And that's going to go out and have each of the workers run the fill model and obtain the predictions for the fraction of data that's persisted to it. And we do that, we see that we now drop our inference time down to about 2.6 seconds, which is overall about a 49% improvement over the standard Dask XGBoost predict. Okay, so now that we've gotten to this point, we've gone through the entire process of building up a local CUDA cluster. We have pulled our data, we've trained a model, and we've looked at the different types of inference that we can do on it. So at this point in your workflow, you should be confident that your model is doing basically what you think it is. You've been able to maybe tune some parameters and you think it looks good. And maybe you want to look at scenarios where you can improve training times, or you can start looking at how the model scales when you, for inference, when you have multiple nodes or something like that. A simple way to do this without having to, go out and, spin up a bunch of additional hardware or something. If you have ad hoc machines, you have some VMs available on site, something like that, you can move over to using something like the Dask SSH Cluster Manager. And so for this, if we do have multiple nodes, in our case, we won't do this, but if we're using multiple nodes with the SSH Cluster Manager, and you don't have something like a network file system that exists on all of the different machines, one thing we are going to have to do is we're going to have to persist our environment. So in this case, Conda, over to each of the machines so that they match the environment we've been using. And we'll probably need to replicate our data set across machines. So it's fairly straightforward. Simple few lines of bash code where we can export our Conda environment, SCP it over the machines, and then create it. And then we can rsync our data set. Much easier if you have something like a network file system, but it's still pretty easy to do otherwise. So then instantiating the cluster is just as straightforward essentially as the local CUDA cluster. We define the nodes that we want to participate as an array. In this case, the first node in the array is going to be our scheduler. And all subsequent nodes are going to be worker nodes that you're going to want Dask to connect to. Then we call SSH cluster. We pass in our nodes. We pass in some type of method to connect to them. In this case, I'm just using RSA secret key. And then we again wrap the cluster we've created with our client, and you'll see something like this, where you see the scheduler come up, and then you see the individual workers being started and connecting back to your cluster. And that's essentially it. Once we've done that, we're back to the same place we were with the local CUDA cluster. All of the commands are going to be the same to train our XGBoost model, conduct inference, and all those kind of things. And when we run those steps, what we see is that we finish training using the SSH cluster. And again, this is just with a single node in roughly the same amount of time for training. We have slightly better predict times, both for the standard Dask predict in place and using fill. And then basically we've scaled up to using the potential of using multiple nodes with the on-site available hardware. All right, so then we get to this point, and now maybe you're looking at, well, we want to scale using different types of hardware. We don't want to go out and buy something without testing it first. So you look at, you can look at like T4s all the way up to, A100 systems, and you can do all that through, provisioning on the cloud. And so in this case, we'll go through an example of how we can use the Google Kubernetes engine to facilitate this process. It'll help when you start to scale to larger production size data sets. You want to improve training times and all those kind of things. All right, so to start, we need to go through a couple steps, or we need to at least outline a couple steps on how we can achieve what we're trying to do in a distributed environment. And so along with the slides, there'll be a more detailed guide that we can link to doing some of these steps. But in general, the process is going to be, we need some form of distributed storage that's shared across the workers and the scheduler. For that, we're going to create a GCS storage bucket along with a service account that has permissions just to read and write to that bucket, as well as create subfolders, things like that. And then you pull the credentials for that service file into something locally that we're going to call keyfile.json. Okay. And once we have that, we've basically set up the kind of the baseline infrastructure we need, so that once we deploy a cluster, all of our functionality will work. So if we're not using a public data set anymore, we can host all our own data sets. They'll be available to all of our workers, as well as the scheduler and everything like that. For the purposes of this example, I'm going to basically assume that we're using a cluster that looks kind of like this. In general, I like to slice off a worker pool, a scheduler pool, and then a K8s pool that is used for the Kubernetes services. And then we basically, we force our workers and schedulers to only go to those specific things based on Kubernetes taints. So in this case, what we're going to do is we're going to create a worker pool that consists of 2 nodes. Each node is going to have 16 CPUs and 2 T4 GPUs. And then a scheduler pool that has 4 CPUs and again, a T4 GPU, and then just a 4 CPU node for all of the additional Kubernetes processes. And then we go ahead and deploy our cluster. All right, so once we get to the point where our cluster is up and running, we've got to do a couple things. The first is that we need to pull our credentials. So it's essentially a gcloud command, which is Google's API, which is going to essentially set up your kubectl utility to be able to talk to the cluster you just created. Next, we're going to create a secret key, or a secret within the Kubernetes system based on our key file that we're going to later use to mount into all of our workers and schedulers, so they're able to access our storage bucket and read and write to it. We'll load the NVIDIA daemon set driver so that the system knows how to configure and provision GPUs within each of the worker pods that we're going to deploy. And then we need to push something that we're going to use as our container image for each of these workers in the scheduler. And so in this case, the container image that I'm using is it's based on the default Rapids container And all I've done is added the GCSFS file system so that the workers are able to interact directly with the storage bucket and those kind of things. Okay. And so this is what our cluster will look like once it's all up and configured. All right, so then in order to configure to launch the Dask cluster within our Kubernetes platform, there's a little bit more work that we have to do. But basically, this just boils down to defining the worker and scheduler specifications. And these are just going to be Kubernetes pod specifications. So there's nothing that's terribly interesting here. All we're going to do is we're going to tell it to mount our secret that we've propagated into the system. We're going to tell, depending on whether it's a scheduler or a worker, we're going to have it declare that it can accept this. It can accept nodes that are tainted for their specific role. That will allow us to schedule all on one system. And so this can be very good for if you're using something like, let's say you spin up a full DGX box because you want to do like a really fast training run, something like that. If you make sure that all of your workers are on the same box, then you avoid kind of off-node networking communications when you're doing scatter gather operations and all that kind of stuff. And so in general, you get an improved and more consistent experience if you make sure that you know where all your nodes are being deployed. Additionally, okay, so then we can specify our container image. We specify the command that it's going to run. This is going to be common for all the Dask workers. Essentially, we tell it we want to launch a Dask CUDA worker that's going to connect back to this specific scheduler, and this is something that's going to be populated by the Dask system, so we don't need to worry about that. We give it some amount of resource constraints, so CPU, memory, and GPUs, and then we're going to set an environment variable that essentially lets the GCSFS file system or library know how it can access credentials to use when talking to the storage backend. Okay, so once we've done that, we'll create scheduler and worker pods representations using Dask Kubernetes, and we'll wrap them in a kube cluster, and then again, wrap that cluster in a client or a Dask client. And at that point, everything becomes essentially the same as what we've done already. Once you do that and your cluster is up and you've scaled to some number of workers, in our case, it's going to be 4. You can use kubectl to basically verify that everything's up and running. In this case, we've got 5 pods, one of which is a scheduler, and the other 4 are going to be workers. And then we have a load balancer, which essentially allows our client to communicate with the scheduler and issue tasks and do all the things that we need to run our jobs. Okay, so now that we've done that, we can see that with the 4-node case, with our T4 GPUs, our training has dropped from basically the initial 130 seconds to 73 seconds. But we also see that our inference tasks have picked up some overhead. And so one of the things you can see here, in this case, some of the overhead is due to the fact that I'm running a remote client. So once all the inference tasks have been completed, in order to return that information, there's some overhead to return the outputs back to my remote client. So some of this can be ameliorated by running your Jupyter notebook or your client in the cluster. And it'll also start to kind of amortize away as you grow to larger inference sizes and you start using bigger models, things like that. So anyway, that's basically kind of the path from going from prototyping on a workstation up to scaling into the cloud. The notebook that's going to be distributed along with the slides should give more detail on this and kind of fill in any gaps or any kind of confusions. And then I have another link that will discuss the specifics of how you configure the GKE infrastructure in detail. And now I will turn it over to Peter Ensheff.
Thanks, Devin. Let me just share my screen. Okay. Thanks, Devin, for the introduction. I will be talking about building a GPU accelerated ecosystem on Dask and Rapids. This is only scratching the surface of Rapids, of what Rapids comprises, but I hope this will give you an idea and hopefully get you excited to try some things out with Rapids. To begin with, this is a view of the Rapids ecosystem, and it's supported and used and extended by a wide variety of partners. In this slide, you see some of our contributors, our adopters, and open source communities involved. I'm sure you recognize some of them, with many presenting at the Dask Summit, including Walmart and Capital One, who will also be talking just after me, so stay for their presentation. In this section of the workshop, we'll go over a few examples of the Rapids ecosystem expansion. Among the examples we'll cover are Blazing SQL, which is a lightweight GPU-accelerated SQL engine for Python, Holovis, a collection of powerful data visualization tools for Python, Clicks, a framework for GPU-accelerated data science and cybersecurity. All of those systems above, they use Dask to scale both in and out. Generalizing, we can say that Rapids always uses Dask in some form to provide scalability to its ecosystem. So almost any time that you hear the word Rapids, you will know that it's being scaled by Dask. Okay, let's begin with Blazing SQL. Blazing SQL is one of the many extensions that helps complement the Rapids ecosystem. It showcases how the ecosystem can be extended by the community to provide blazing fast solutions to various data science applications. Being built upon Dask and cuDF, it also enables users to conduct ETL and analytics, allowing data frames to be passed along for further processing to libraries such as QML and cuGraph. Blazing SQL has already been used by various initiatives and working groups. It was a key component during the research on COVID-19 on the Summit supercomputer, which is a supercomputer located at the Oak Ridge National Lab. To give you a glimpse of what we can do with Blazing SQL, imagine, for instance, you have a cuDF data frame imported from a CSV file. From that data frame, we can create a Blazing SQL table. In this case, we named that table taxi, and we are then able to execute SQL queries on that table. The query we execute here is simply counting the number of entries of the SQL table, which roughly translates to rows in a cuDF data frame. This will result in a cuDF data frame that can be used for further processing with further ETL processing with cuDF or even Blazing SQL itself, or be passed along to other Rapids libraries for further processing, such as QML or cuGraph, or depending on your application. This is how Blazing SQL easily integrates into other end-to-end Rapids workflows. You've already seen this workflow at an earlier stage on this workshop during the section presented by my colleague Vibhu. And Blazing SQL can be introduced as the same workflow, where it acts as another layer between the user's data and the ETL phase with cuDF. So Blazing SQL is pretty much built upon cuDF and returns the same type of data, so you can mix and match them both, and it feels like it's just a single tool. Getting started with Blazing SQL. Sorry, I'm hearing some feedback, so could you mute, please? Yeah, thank you. Getting started with Blazing SQL is very straightforward. Initially, we instantiate a Blazing context. With that done, we can then import the user data. The data can be located at a local storage unit, but we can also use data lakes such as S3 and HDFS because they are natively supported too. It enables users to easily take advantage of the data on the cloud. In this example, we see the data being imported from an S3 bucket for which we create a table named taxi. This data set is part of the New York City taxi that is publicly available. So I'm sure many of you have come across that at some point or another. After creating the table, we can execute SQL queries on the data frame by using the SQL method from the blazing context object. With the query in this example, simply selecting all the entries. We then call the tail function. The tail function results in a QDF data frame and is then presented with the last few rows of data. So it looks exactly like a pandas data frame output when you print in a notebook. The previous example was using a local single GPU workflow. We can, of course, scale that in and out with Dask. In this example, we begin by creating a local CUDA cluster with Dask CUDA. Dask CUDA is the CUDA-ware implementation of Dask, where by default, there will be a Dask worker for each of the GPUs available on the system. We can then connect a client to that cluster and create a blazing context connecting to the Dask client. From there, we can work with the blazing context the same way as we would with a single GPU context without Dask, as we've seen in the previous slide. Still in this example, we ingest multiple local CSV files and create another table named taxi then, and finally execute a SQL query on that. Note that in this case, the returned object is a Dask QDF data frame. So this is similar to a pandas-backed Dask data frame, where the data is distributed among all Dask's many workers. Okay, let's talk a little bit about visualization with Rapids now. cuCrossFilter is another library written by the Rapids team, and it provides seamless integration with other libraries from the ecosystem and is very easy to use. It allows users to create fully cross-filtered dashboards in a few lines of notebook code. cuCrossFilter provides fast visualization and a highly customizable layout and themes, which makes it very interesting to create your own applications with visualizations. To get started with cuCrossFilter, let's take a look at this example here. In this example, we begin by creating a cuCrossFilter data frame from a QDF data frame. Note that in this example, we build upon the previous blazing examples that we've shown before. So we are still selecting some columns from the taxi table, and this will return a QDF data frame. Thus, we are actually creating the cuCrossFilter data frame from the QDF data frame returned by blazing. We then move on to create a chart and define a dashboard. In this case, we are creating a scatter type of plot that is two-dimensional with X and Y axis based on the drop-off location on the data set. And then we create a dashboard from that scatter plot, and we display the chart. The resulting chart that we get can be seen in this plot. And the lighter green and yellow means higher density of points, and the blue points represent lower density in this case. Now, the HoloViz ecosystem provides massive scale visualization, integrating QDF and cuCrossFilter in its ecosystem. HoloViz allows to easily annotate and interactively explore data with minimal syntax and accelerated server-side rendering for high-density visualizations. Integration between HoloViz and Rapids continues to be worked on, but we will still see a few examples of how users can benefit from that integration already today. So let's begin with a data shader example. After importing the implementations we need from data shader, we define a query. This is another Blazing SQL query. We are still building upon the same table that we've seen in previous slides. And for those who are not familiar with SQL, mostly like me, but this is pretty simple. We are still selecting two columns, drop off X and Y, from the taxi table, where the pickup time is between 6 a.m. and 15 p.m. or 3 p.m. actually. Then we define a canvas mapping each point as a pixel. So we execute that query, which will again return a QDF data frame and be passed into the points method from the canvas object. We then say that we want to pick drop off X and drop off Y columns. And finally, we generate the image from that QDF data frame. Notice that we are taking the points, and we are also specifying a color map fire, and we want the background to be black. So the resulting data, the resulting plot looks very similar to the previous plot that we seen with Q-cross filter. But now we have filtered data a bit differently, so the final representation is not exactly the same, although you can see the similarities quite clearly. Then we have an example with hollow views. Again, we import all the necessary parts, and then we define an extension with bokeh, and we instantiate some default options. For example, that we want a scatter object of sizes 425 by 425 pixels. And then again, we need to provide us a Blazing SQL query. So now we are doing something a bit different. We're selecting the fair amount and the tip amount from the taxi table and using the same names for the columns. And then on the lines just below, we want to specify a range. So we want to filter out everything that is not between $0 and $100. So this will be our final plot, will be only within that range. We specify then the color map, cool, warm, and finally the labels that we want. And we then generate the image, of course. And finally, the resulting plot then represents the amount on a range from $0 to $100 on the vertical axis, the tip amount, sorry, and the fair amount also on a range from $0 to $100 on the horizontal axis. In this case, higher density of points is represented by the red part, with blue representing the lower density points. Then we move on to Plotly. Plotly Dash is a Rapids accelerated deployment of Dash apps. It is another library with constant improvements on Rapids integration, with new features and capabilities rolling out frequently. Unfortunately, we don't have much time to go over a Plotly example in this talk, but there's a presentation entitled, I think, Architectures for Scalable Analytic Dashboards in Python with Dask distributed and Dash in the Dask Summit. So be sure to check that out if you're interested in Plotly. Let's now move on to the cybersecurity topic. Recently, Rapids has also joined the cyber threat combat that can now be accomplished using a new package called Clicks that I mentioned earlier. Clicks is a set of examples and capabilities to bolster cybersecurity professionals. It's built upon Rapids, and as seen on the figure on the right, it easily integrates with various file storage formats and services with existing data science, machine learning, deep learning software, as well as third-party security intelligence services. As with other Rapids software and tools, Dask is a critical component to Qlik. It allows it to scale stream processing and analysis capabilities. So again, it's a very important piece of Rapids. On the right side, on this slide, we have a table containing several of the examples that Qlik includes today. These examples allow cybersecurity professionals and data scientists to easily experiment before Qlik, professionals were likely required to have good familiarity with GPUs and accelerated computing to devise an HPC system for that. Now Qlik intends to remove that barrier and let professionals focus on solving their problems efficiently. Recently, NVIDIA announced a new cybersecurity framework called Morpheus. And the new Morpheus framework is also leveraging Qlik to help operationalize models. The plan is to have Morpheus open sourced as well later in 2021, so watch out for that soon. At this time, we are still not open source, but we will be. And while Qlik is a great set of tools to experiment, cybersecurity professionals will also want to operationalize the results. To do that, we build on other ecosystems from communities out there. So users can quickly experiment and fine-tune their models with Qlik and then convert their models with Onyx. The resulting model can then be operationalized by loading it directly into Morpheus via MLflow. Okay, so this is the Morpheus architecture. Morpheus is built on top of the NVIDIA EGX stack. The EGX stack delivers a platform for machine learning, deep learning, and HPC. Included in that stack is, of course, Rapids, and by association, Dask. Morpheus is divided in 3 phases. The first phase is the perceive phase. It consists of the input data. It can come from application logs, from threat intel, from security information, event management alerts from applications or network hardware or anything else that you can imagine. The second phase is the infer phase. It consists of four steps. The data preparation is the ETL step, where we can use various of the Rapids tools we have covered already, Qlik, CoolStreams, for example. Inference is the step that uses the Triton inference server. I'm not covering this here, but Triton inference server deploys trained AI models from any frameworks, such as Onyx. And then we follow to the post-processing step that produces metadata with Rapids and Qlik. And we go to the verify step. This is typically an optional step, but it would, if you include that, it would generally have any routines to help verify or instill additional confidence in the output of your model. The third and last phase is the act phase. This is the final phase of the workflow used to provide feedback to the security application or device. This can be a straightforward action, such as telling the application to isolate the offender, or it can be used in conjunction with Rapids and Qlik to form a more complex JSON message, for example, and then you pass on the data to your sink. A typical application to detect anomalous behavior with Morpheus is exemplified in this slide. First, we pull specific data from Kafka that we then turn into NumPy arrays that are passed into the inference step. In the inference step, we convert the NumPy arrays to QDF and do any necessary ETL on that data. followed by running the inference on the Triton server that will apply your model, basically. The predictions made during inference are then directed to the application in the output phase. Okay, so this is a summary of what we have covered in this talk. Rapids is the ecosystem providing GPU-accelerated Python libraries for data science. Blazing SQL provides a SQL library. Cross-filter dashboards. HoloViz provides massive visualization libraries. Plotly provides Dash apps. Clicks provides is a package of examples and tools for cybersecurity. Morpheus is a cybersecurity framework, and Dask is used in all steps to enable Rapids to scale any of those cases that users need more than a single GPU. Thank you for listening. I will now pass the word on to Rich Ulrich from Walmart Global Tech. He will talk about solving challenges in the enterprise with accelerated data science. So please hold on for him.
Thank you. Let me share my screen.
Let me stop sharing. You should be good.
Okay, hopefully y'all can see my screen. Very happy to be here today. I wanted to kind of talk a little bit about some of the work we've done with Rapids at Walmart. As mentioned, we are participants in the community and help contribute and actually participate quite heavily within Rapids community. We believe it's something that's very worthwhile to business organizations. The reason we do so is, as you all may know, Walmart's a rather large company. We have quite a few stores, over 10,000 worldwide. I think that this is a fairly old, so I think we're quite a bit larger now. But some of the things that's interesting about Walmart is about 90% of the population in the US lives within 10 miles of a Walmart store. So most of you on this call probably live pretty close to a Walmart. We serve a lot of customers, both on e-commerce and in our stores. So way we look at this, and this was kind of entailed in some of the conversations, is we look at the Rapids ecosystem as multiple components that work together well. And from that, I mean, especially if you're looking at ETL, which is a key to actually preparing your data for any data science. And without data, there is no data science. So it's a key to everything really a business needs. There's three tools that I kind of want to talk a little bit about and kind of how we use them in conjunction. And that is QDF and Dask QDF. Blazing SQL, BSQL is what we always call it, and then Dask. So basically QDF is the acceleration of using GPU of your database functions, your ETL functions, your feature engineering. Basically, it's a replacement for pandas. It was kind of mentioned by Peter and others. It's a key to scaling up data science and features engineering. Dask allows us to scale out to multiple GPUs, and Blazing SQL is an SQL engine built on top of the Rapids ecosystem. The way we think about that is all three of these tools can be used together with different problems. So it's kind of like a tools in your tool belt. You may have certain problems, and because they all work with regard to data frames, you can actually use data frames. You can use SQL, turn it into a data frame, and then take that data frame and join it to a data frame that was created in QDF and extend it across with Dask and do all sorts of different combinations of things. So I want to talk a little bit about kind of what we're seeing with this and kind of why it's a key for us. As I mentioned, our scale. we actually look at this to try to scale our data and our data science and accelerate it. Some of the things we started off doing is initially looking at Dask QDF, and we've actually started doing, as I mentioned, looking at the combinations of how we interoperate different pieces together to try to solve problems. Not just looking at Blazing or not just looking at Dask QDF, but looking at different ways that we can do things. One of the things we've noticed is we've realized is if we understand our data very well, we can do things like create multiple Dask workers and then have Dask QDF, QDF work under each one of the Dask workers and actually segment the data out as long as we know that data portions is independent, and we can avoid a lot of shuffle. So one of the ways we do this is something like with partition by hash, where we know we're going to do certain operations on data. We can hash it and partition it a way that makes sense, and then use Dask workers to work each one of those pieces or each one of those partitions independently, and thereby avoid a lot of shuffles on the data. This actually speeds up things even more. Another thing that we've learned is we try to focus more on our more resource intensive workflows. We have a large amount of data, and some of them we do a lot of computational operations. Some of them we don't do as much. They're more IO bound. So we've started honing in more on ones that do more computational, just because of those are the ones that really see the benefits of moving towards accelerated compute. I think they all may eventually see a benefit, but doing so and being able to prioritize the ones that give you the most benefit actually is just a kind of a good way to start implementing this. So we try to avoid the ones that are IO bound and focus more on the ones that are compute bound. And another thing, because Rapids is a open source community, there's a lot of features that have been implemented, but there's still others that haven't been implemented yet. So keeping your finger on the pulse of what's going on in the community, understanding what features you need, and working with the community to help get those features enabled, and avoiding utilizing workflows that have features that are not enabled is a couple of things that we do. So we kind of do both. We try to avoid changing production things with things that don't have features yet, but while still working with the community to actually start building out those features we'll need eventually. So I want to talk a little bit about the results we're seeing. So this is our finance daily sales. As I mentioned, we have quite a few stores. So this is actually accumulating a lot of the KPIs and the metrics we need that the business uses to make business decisions down for every store, every item that we have. And we have about 1 billion store item combinations. So this is actually quite compute intensive. So you'll see on the left-hand side, this is actually about 11 jobs that run sequentially. And using Spark and Hive, this was the way it was originally built. Those 11 jobs take about 53 minutes. When we converted this over to utilize Rapids, we dropped that time frame down from 53 minutes to about 7 minutes. So we got about an 8x performance improvement, but we also reduced our hardware requirement as well. So actually, this actually allows us to see a benefit from a total cost of ownership as well as a performance benefit. One of the things that we used with Dask, we thought was kind of a benefit that we didn't foresee at first, was each one of these workflows, generally the way they were written, would do their particular work and they would write their work out to disk. And then the next work would read in the output of the previous job and process it. And so they were chained together that way. Dask, and utilizing Dask and dividing the work up appropriately, allowed us to chain together those jobs and keep the data in memory. So the output of one job was thereby started processing with the next job, just utilizing a Dask graph. So we avoided a bunch of I/O when we started looking at things like this, and it actually allowed us to improve it even more. Similarly, we did the same type of thing for finance hourly sales. This one, however, runs instead of once a day, runs 24 times a day, 7 days a week. Similar types of jobs because it's similar KPIs that's used for the business, except here they're looking at hourly as opposed to daily accumulations. These again were run, and previously it would run 24 minutes is how long it would take. So if you can imagine, every hour I would have to run this job, and it would take 24 minutes of the hour to actually run it. And so if you're thinking about something in a production system, that means if I had an issue, basically I have one shot and then I miss my SLA because I have to have this done within the hour. But with Rapids, we actually can do that in 3 minutes. And again, we lowered our cost of ownership, which allowed us to actually look at how we can improve what we do for our customers. We tend to try to take anything that we make and we give it back to our customers in the way we offer services to them. The last one I want to kind of talk about was looking at product substitution for our merchants. And this is an algorithm we utilize internally to understand similarities between products. So if you think about, say, coffee, if a certain size that you currently want is not there, will you buy a size of the same coffee, a different size of it? So this is trying to understand from our modular perspective what items we need to keep on the modular so that we have the products there for the customer that they want. This was something that again took a very long time to run. This per category, it took about an hour and a half, almost 2 hours to run. We have about 2,000 or 3,000 categories. So this was very time intensive to run this algorithm. We actually converted the entire algorithm to being run utilizing Rapids. And again, we saw the same type of benefit where we took almost a 2-hour run down to about 27 minutes. Now this is on average. We have some very large categories, some small categories, but on average this is what it does. And it allows us to run substantially faster and lowers the cost of ownership. And all of these things, Dask plays an integral part of it, as long with Rapids and the different tools within it, because we always have to think about not just the side of scaling up or making things faster, but because of our size, we actually also have to consider how we scale it, because we if you have 10,000, 11,000 stores, you can't just look at, a small slice of data. It's always a lot of data. One of the last things that I kind of want to talk about is we actually utilize the Rapids ecosystem in Dask to do things where we simulate our supply chain, and we try to make business decisions about how to improve our supply chain. So in this particular scenario, we are looking at how we can minimize or maximize our profit by impacting a couple of decisions that we have on how we do things in our stores. So this is as simple as the size of boxes we ask our suppliers to send us. So if we have a larger box, do we have more touches? Do we have more inventory? And actually trying to understand the trade-offs between touches touches, how often we have to handle that merchandise as it goes through the supply chain, so it costs labor, versus having excess inventory across our stores. So we're looking at the cost of goods, our labor, and our inventory. And we're also looking at our facings. So in other words, if you look at the way the products are in the center section, that is cereal. So the reason they're stacked like that is we would tend to sell more of our Frosted Flakes at this particular store than we would honeycombs. So we're trying to ensure that the product is never out for the customer. And because of we don't know the demand each day, we tend to put more facings for the more frequent something sells or the faster selling it is. So we're trying to actually optimize both of those. And to do that, we look at all the parameters that we have across our stores that impact both the facings as well as the supply chain. And we go through and simulate all the sales and all the labor across all the stores and look at the parameters that impact our decisions for the facings, which is a local decision, and the pack size. And we take all of that and we try to optimize and make decisions so that we can tell the business partners what the right size pack should be, as well as what the facing should look like in each individual stores. The pack size is a global decision, the stores is a local decision. We actually have it ends up being about 5 quadrillion parameters, or actually 5 quadrillion days worth of simulation that we have to do because of the store item combinations that we have. And with all the parameters and all the different pieces of it, we actually can process this. Now, this is for a very small category. So if you kind of look on the left-hand side at the bottom, this is 129 items in a very small category across our chain. That 129 items grows into about 755 billion days worth of simulation. To do that whole thing utilizing Dask and Rapids, we can do that in 53 seconds. So we still have to do a bunch of them, but that kind of is a subsection of kind of what the Dask and Rapids allows us to do to make better decisions for our customers, to ensure the right products on the shelf for the customers or yourselves when you walk into a store. That's all I have. And so I guess I will stop here and turn it over.
All right, Rich, thank you so much. Appreciate you attending and appreciate you showing some of the cool work that you're doing at Walmart. I'm going to pass off to my former colleague, Mike McCarty, who works at Capital One, the Center for Machine Learning there. Talk about some of the cool stuff that they're doing with Dask and then also adding on Rapids there. So Mike, when you're ready, you can share your screen.
Alrighty, give me just a second here. All right, can you see my screen?
Yep.
All right, great, thanks. So yeah, I've got a couple slides and then a couple of other articles, and can walk you through some kind of code examples even too of some of the work that we've been doing with Rapids at Capital One. I've written a lot about this. So just quick intro. My name is Mike McCarty. I'm a distinguished engineer, machine learning engineer at Capital One. I lead a machine learning tools group that's focused on building out internal libraries for data scientists and machine learning engineers throughout the company. We're in a center of excellence called the Center for Machine Learning, and we work with various lines of businesses to make them efficient and successful. And we've been helping them get some wins with the Dask and Rapids tech stack, And I'll go through a couple of case studies there to talk about some of the performance gains that we've gotten. Just to kind of set the stage a little bit for the landscape at Capital One, it's kind of like what was being described there at Walmart. We have a lot of data. We have a lot of data scientists and machine learning engineers that are doing things with that data, building models, trying to build better models, more predictive models for various reasons related to like credit risk assessment or loss forecasting or all kinds of things that one can imagine a large financial institution would do with machine learning. We have a wide variety of data, whether it's CSV files, Parquet files, SQL databases, Avro datasets, Hive data stores, all kinds of things like that. So data access and data transformation is always a challenge. And so yeah, that's basically the landscape. As a data scientist at Capital One, you're going to work with a lot of different languages, the kind of standard stack that you see in the community. It's about 50-50 between the Java ecosystem, Scala ecosystem, and then Python is kind of the emerging player. And so there's more and more Python analysis all the time, and scaling Python at Capital One is really, really important to us. And so that's where this stack comes in and can be very, very beneficial to us. Some other challenges due to scale is education and training. So we do a lot of work internally with our internal tech college and other university partners to train up our data scientists on this stack. We give tutorials internally and contribute back to those tutorials. A lot of times we're giving Rapids or Dask tutorials, the same ones that you see in the public. We'll give those internally and then make them better for financial or just various institutions. So that's another very important aspect of what we do. We've deployed Dask and Rapids pretty much any way one can, apart from the HPC systems, because we're a cloud-first company. So Dask deployments has always been an area that we've been interested in, and Rapids deployments. So yeah, that's kind of like the landscape. I'm going to get into a couple of use cases and walk you through some examples here real quick. So what I'm showing on my screen here is an example pipeline that we started working with. This isn't the real pipeline. This has just been kind of generalized, but you can see the different steps. You can see some of the stuff that was discussed earlier. Like we've got a lot of to CSV and read CSV here between each one of our steps. So we've got a lot of data serialization going on, pulling data in and out of memory, writing to disk between each steps. If you were to open up, one of these steps, you'd see something that looks somewhat like the code snippet you have here. You're importing pandas, you're loading, loading the data with read CSV. You're going to do some pre-processing on that data, and then train a model. So you can see here, literally looking at the PyData stack here without Dask or Rapids. We have some stats here on the amounts of data we're looking at and how long it takes for this pipeline to run or parts of this pipeline to run, and kind of like the general lay of the land. So a lot of room for improvement. One could argue here, we've got 40 gigabytes of training data. You can easily get that on a single system on AWS today. So that's actually what we see happening is a lot of practitioners within the company are standing up a large instance and just kind of waiting and letting this pipeline run. And they can go about their business and you can generally make progress there, but it's not as fast as it could be. And so that's where my team came in to try to figure out how can we make this better with this tech stack. All right, so moving on, basically where we start at in optimizing this pipeline, and I'm going to walk you through that here. We start with just like the sample step of like sampling the data, doing some of the pre-processing before we go to feature engineering. Just with Dask alone here, we see that we can get in this particular pipeline, we got some pretty significant speedups here. We have a lot of joins, a lot of serialization happening in this script. This was taking 7 days to process. It was on about a terabyte data set. Just using Dask data frame to parallelize some of this this pipeline, here are some of the speedups we're able to get. And so that was very exciting. And this was just kind of an initial kind of dipping our toes into this tech stack. And so we went on to kind of parallelize some of the other parts of this pipeline. And so here are some of the results that we saw from doing that. Just performing grid search on even a local cluster, we can get some pretty significant speedups. So the nice thing about this is we can take this one kind of bit of code, and we'll get into this in a minute, and be able to scale it now on all these different kind of cluster topologies, whether it's GPU or CPU in a single instance or multi-instance. Getting into training a little bit, this is where we started to get into GPU training with Rapids using XGBoost. We were very excited to see the GPU support there. And so the training data set that we were using here was actually 4% of the total available data. So that was like a common pattern that we would see with the data scientists. They would actually downsample the data to do their iterations to like figure out what kind of model, what kind of hyperparameters they want, and then scale out to the large data set. But sometimes they didn't need that full data set. They would actually just only use 4% of the data. But the question was always like, what kind of model could I get if I used all my data? And so 4% of the data is what was being used initially. We saw a 100x improvement in training time for that size of the data. In the 97 reduction in cost there. The interesting thing about that for this particular model, when you're running on the cloud on a GPU instance and you're not getting a dedicated instance, you're essentially renting a GPU or a system with GPUs. In this case, I had multiple GPUs. If you're renting that system and your cluster is fairly elastic, you can scale up and down quickly. You're only paying for the GPUs during the training time, and so that was a huge factor in this cost reduction. Rather than having a large memory instances sitting there, running for days on end, you're running a GPU system for under an hour, and so it's kind of counterintuitive because a lot of folks think that GPU computing is expensive, and now GPUs are expensive. Yes, we know that. But when we're renting them on the cloud and we only need them for a much smaller amount of time, it actually becomes a cheaper solution. Another interesting thing we did here was we wanted to do a study of how XGBoost scaled as we added GPUs to the training. And so that's what the plot is there. And then we threw in the original training time on that instance that we were using, and that's where we get the 100x speed up. And notice that's a log scale. Getting into some of the costs a little bit more. This is what we saw as soon as we got into a multi-node situation, mainly because we were only using 4% of the data set. We wanted to scale to the full data set. It was a 1 terabyte data set. We initially oversized the cluster to, I believe it was, where is it on here? Oh yeah, it's right there. It's 16 GPUs. No, I don't have it on this slide. Sorry, that was another slide. We initially oversized this cluster, and this is the final number we used. We actually had like 12 instances, I think, at one point. We only needed 2, and that's due to GPU memory to system memory spilling. But the nice thing about this that you see is we were able to beat, in time, we were able to beat the original training data set with the GPU solution. It was going from 2 to 3 hours down to 22 minutes, but that's on all the data. and the cost was just a little bit more. And so now the question is this a better model, and what can we do with that? And that's very, very important in finance to find a better model, because that equates to real dollar values. So that's what I wanted to kind of recap there. You can read more about that in this blog. Happy to send this, or Jake can share it out. Another thing I want to touch on is, what do we do? So this is great. This is exciting. This is some initial work that we've done with this stack. Now, going back to what I was describing before at Capital One, we have like a lot of data scientists. There's we're trying to teach them how to use this stack. How do we kind of upskill the entire enterprise to be able to leverage this technology? And one of the ways in which we've been doing that is by showing our data scientists how to kind of package up their code in such a way that their data analysis code in such a way that it's reusable, but it also scales both on Dask and on Rapids across the accelerated and the distributed paradigms. And so that's what this blog article is about. I've got a lot of code examples in here, but this talks about how we're building our own custom estimators that scale with Dask and Rapids. And so essentially the idea is you're building your own scikit-learn estimator. You can pass in a Dask collection or a Rapids collection, and we're handling some of the logic around the differences between those two things. Sometimes we're converging on a common data structure, whether it's the array interface or the data frame interface, and then building out kind of our core logic within the scikit-learn API, and how we can then build these reusable components that we can then chain together. And then we build a library around those components, or other teams build out their libraries following the same pattern. And the idea is we were able to reuse code, but also share code between teams across libraries. And so that's what we're trying to do now with this tech stack. So it's completely changed the way in which we're writing code and maintaining code within the enterprise. One other example that I'll share real quick, that I've talked about a couple times. Here we're in a situation where all of our data fits into memory on a GPU. It's under 16 gigs on like a P3 instance on AWS or something like that, on a V100. And we just want to expand our hyperparameter search. And in this case, it's an XGBoost model that we're training that has been accelerated. And so now what I've done is just defined, I'm walking you through in this example, and this is all on GitHub, an objective function in Optuna, or an objective class in Optuna, that is handling some of the data ingestion. And then the call method is implementing kind of the hyperparameter tuning. And you can get really fancy with this with Optuna, as fancy as you want. It's just Python code. And so essentially that's just going to be my objective function, right? I'm generating some data here just for illustrative purposes, but you create that objective function, or that objective class, you pass that off to Tuna to run a study, and it's going to maximize the accuracy that's returned from whatever that function is. So that's kind of the base premise here. And then you can look at your best trial and all that kind of stuff. Well, what we've been able to do actually here is parallelize this, run this objective function in parallel, but on the GPUs, because again, we're training with XGBoost. We're passing in the GPU has true method, but all of our data fits into memory on the individual GPU. And what this logic here, and this is like, there's probably a better way of doing this, but this is just kind of an example of something we've been able to do. Every time you call this function, it's going to pick the next GPU, and I've got 8 of them on my system, say. It's going to load the data on, and each trial will run on that GPU, and we'll just round robin. And with this, since we're training on GPUs now, each one of our GPMs build a lot faster. That means we can expand our hyperparameter search space and find a better model. And again, that's really important to us here. And in this case, where all of our data fits onto a single GPU, we can now rapidly expand our hyperparameter search. And with something like this, we're able to train on our data set, we're able to train like 300 GBMs within 24 hours. Again, that's like $600 on this system, something like that, $600, $700. that's very much worth it to be able to find a better model. And I can do that within 24 hours. So that's a huge win for us. That's all I had, Jake. I'm happy to answer questions, or we can move on. Thanks.
So I think since it's been a longer session, let's allow folks to drop. I do have just a few closing things. So someone asked already in the Slack channel, or rather not the Slack channel, the messaging on Zoom. We'll put this slide deck into the Dask Slack workspace that we have for the workshop. It's going to come with some slides at the end that kind of helps you see how you can get started with Rapids, documentation, some resources for helping you self-start, and also ways to get in contact with the Rapids team or just get some feedback to us. And then also, we really do hope to use that Slack workspace, the workshop workspace, to continue conversations. There's already some going on right now in the space, so we welcome questions from the Dask community. And also, we do have other, kind of NVIDIA supported talks, whether they're kind of NVIDIA particular tools or they're NVIDIA contributors to the Dask community, talking more about open source things. So in that presentation, you'll be able to click on this link at the bottom and go to some of those presentations and see what's going on. Also after this, I think as you can see on day 2 here, there's actually a tutorial for Dask and Rapids. So at 2:30 Eastern time, 11:30 Pacific, there will be this tutorial. So in just about 30 minutes, if you want to learn more, a little bit more hands-on, that tutorial will be really helpful. So just like to thank everyone who spoke today, both the NVIDIA folks, Rich and Mike, we really appreciate it. And yeah, I hope this was really informational for folks, and I'm sure we'll talk soon.